Now let's talk about CAP theorem. It's a very popular theorem that relates to databases or distributed databases. And frankly, for how popular it is, it's a very poor theorem. It's really widely misunderstood, and it's not as helpful as many people think it is. For more details on why that is, I would check out Martin Kleppmann's blog post about CAP theorem. It's not super long, but I definitely think it kind of raises a lot of really good points that I'd mostly agree with. But I'm mainly going to be echoing a lot of the points that Martin Kleppmann makes. So first of all, it applies to some distributed data. Like let's say we have a database, over here. If we just have a single database, it doesn't really apply. It mainly applies when we start replicating data. So for example, if this is the leader and this is the follower, then we can sort of apply a CAP theorem. But mostly people apply it to NoSQL databases because they have replication by default. But a lot of times people will try to apply CAP theorem to just a regular SQL database with a single node, no followers, no replication, and it's not really sensical in that case. So that's what I want to mention. I bet if you've learned about CAP theorem before, it wasn't mentioned to you that it only really applies with replicated data, though it's kind of implied. So we have an acronym and it's pretty simple. C is for consistency, A is for availability, and P is for partition tolerance. And what people think is that from this acronym, we can choose 2 out of 3. So we could choose CA or CP or AP, but the problem is that that's not the actual theorem. But the problem is that P is actually implied. It's always going to be a part of our choice. So the real theorem is that P is guaranteed and we are allowed to choose either C or A. Like that's the most we can do. But I guess before I get into too many misconceptions, I should tell you what the theorem actually is, which is in a distributed system, if we have some replicated data, think this is our leader database and this is our follower database. First of all, partition tolerance, which is poorly named, I think that's where a lot of the confusion of CAP theorem comes from. People don't know what exactly partition tolerance is. It's actually very simple. We have our distributed system here. We have 2 databases. One is a follower, one is a replica of the leader database. And of course, we could have a lot more followers, we could have a lot more replicas, but this is a simple view for now. And this is our network. We have 2 nodes in our network. Of course, the leader is going to be backing up data. It's going to be copying data that's written to it, to the follower, to the replica. But the problem is if we get a partition in this case is a network partition, that means that our system here of 2 nodes gets cut, it gets partitioned, and then we have these 2 databases. One is a replica of the leader. Now these 2 databases can't talk to each other, so we get some type of network problem. But maybe users can still interact with this database and some users can still interact with the other database. So this is a partition in this case. Partition tolerance means that our system will continue to function if our system becomes disconnected in some way. If one half of our system can't communicate with another half, or maybe we had 10 databases and one of them was disconnected from the other, it could be any type of network partition. So we could decide that because our 2 databases can't talk to each other anymore, we're just gonna, not let this entire system function. We could decide that, but the vast majority of the time we do not. That's why P is guaranteed. Just because, our 2 databases are disconnected doesn't mean we want to prevent users from being able to interact with them. So assuming that we are partition tolerant, just because our system gets a network partition, that we will continue functioning. So that's implied. This is almost always assumed. Then we can only choose between one of these. We can only choose one of consistency or availability. Why is that the case? Well, let's first understand what consistency and availability actually means in this context, because another poor thing about the CAP theorem is that these terms are not what you expect them to be. That's where a lot of the confusion comes from with CAP theorem. Though I think it still can be a decent tool to reason about the trade-offs when it comes to choosing which database should be used to solve a particular problem. But in this case, consistency actually means data consistency between the replicated data. So we know that this leader is going to have data written to it and it's going to copy all that data with the follower. Now it might be asynchronous. It might take some time for the leader to replicate that data, but it will do so. But consistency in this case means that every single read will get the most up-to-date written data. So if somebody actually writes data, like while our system is partitioned, if somebody writes data to, the leader database, and then somebody reads from the leader database, then they will get the most up-to-date data. But while our network is partitioned, none of the data from the leader will be written to the replica. So if somebody reads from the replica, they will not get the most up-to-date data. So this is an example where we do not have consistency. Every read does not get the most up-to-date write. This is a different consistency from ACID. It's slightly different. With ACID, consistency meant that, a single node has consistent data, right? Consistency with ACID does not apply to replicas. We don't need replicas to talk about ACID consistency. Okay, but what about availability? Well, it's pretty similar. When we have a network partition, we know that one of the replicas or many of the replicas may have out-of-date data, right? That's what we learned with consistency. So now the problem is the choice that we have, we can say, well, since this replica is not going to be able to get the most up-to-date data from the leader, how about we just disallow users from using just the replica? They can continue to read and write from the leader, because we know that reading and writing from the leader is going to have consistent data, right? It's going to have the most up-to-date data. People can write to it. People can read the most up-to-date data. But we only achieved this consistency by giving up availability, because availability in this case does not mean highly available. It doesn't mean that 99% available or 99.9%. It doesn't mean, what percentage of requests are going to get a valid response. That's not what availability actually means in this context. It means for our system to have availability deemed by CAP theorem would mean that every single node in our system, every single database node, including this one that does not have the most up-to-date data, every single node will respond to valid requests. So if this database does not crash, we know that this database did not crash. We intentionally said that this is not going to be responding to requests anymore because it has stale data. But it did not crash, and we say that every database that does not crash, whenever it receives a request, it responds. So every node in our system is available to respond to user requests. That's what it means. We're not talking about 99% or anything like that. We're talking about every node that did not crash is going to be available for users. So looking at it this way, it becomes pretty obvious when we have a partition why we can only choose one of these. We can only choose to make all of the nodes available for users, even if some of them have inconsistent data, or we can decide to intentionally, stop these from serving users to ensure that all the nodes in our database that are serving users have consistent data, that have the most up-to-date data. So there it is. That is CAP theorem. So when it comes to designing databases or choosing which database to use for your application, the important thing about CAP theorem is that we can only choose between one of these. We might not be able to choose either of these, actually. It's not guaranteed that we get 2 out of 3, but the thing is that we have to make a strong consideration between consistency and availability. What matters more? In many cases, it's okay if we have inconsistent data, if we have some stale data, like with Twitter follower counts or something like that, as long as we are able to handle more traffic, because that's what availability is still about at the core, right? We want every node to be available because we want to be able to serve a larger amount of users. And that's really what you gain from CAP theorem, because technically when you get really, really technical, very few databases are actually CA meaning they have these 2 out of 3, or AP, meaning they get these 2. Very few databases actually, rigorously fit these definitions, which is why it's better to keep things simple and just focus on the consistency versus availability trade-off that you have to make, and kind of understand why that is, because at the core, it is pretty simple. A lot of times people will visualize CAP theorem using a Venn diagram, even though, that region where you have all 3 doesn't really apply. That doesn't really exist. You can't really have all 3 of these. It's kind of just a logic problem if nodes can't communicate with each other. We can't, of course, guarantee these two. It's just a contradiction. And lastly, let's finish up by understanding maybe a slightly better theorem. This is actually an extension of the CAP theorem, PACELC. PAC, that is basically, CAP theorem still. It means, given a partition, if there is a partition, because, not always is there actually going to be a network partition, but it's always possible because networks are unreliable. A network may always go down. One data center might go down, somebody's router might go down, anything could happen. So when there is a partition, let's say yes when there actually is a partition, or versus no when there's not a partition. So when there is a partition, we can only choose between A and C. We can choose between availability or consistency, right? We can choose to favor one of these. But if there's actually not a network partition at any given point in time, at some point in time, there's not a network partition right now. So actually, if there's not a network partition, why can't we choose both consistency and availability? Well, we actually did talk about that for a brief moment. When we have a database and we are replicating that database, it takes time to do that, right? So if this is our replica and somebody is trying to read data from this replica, but it's taking us some time to back up the database or to replicate the database, we have to, for that user, favor two things. Either we favor latency or we favor consistency. Either we let the user read data immediately, but they might be getting stale data, right? That's a trade-off that we make. So we favor latency. We, get low latency for the user, right? That's what L means here, low latency. Or we give them consistent data. We give them the most up-to-date data, even if they have to wait a few seconds for us to replicate this data. So that's why I think this theorem is actually a little bit better, because it gets at what a lot of people think of when they think of CAP theorem. A lot of people are probably thinking of latency, even though CAP theorem does not have anything to do with latency. The follow-up theorem does. But at the core, these theorems are not about us writing our own computer science paper. It's about us understanding what trade-offs we can actually make, what trade-offs we have to make when designing a system, when designing a distributed data storage system.